going to end this section, whatever we're in. I've lost track of my section numbers. 5.4. So we're going to end 5.4 by looking at some examples of the average value and the mean value theorem for integrals that we developed last time. So go back and watch those videos, but I'm going to go ahead and jump in with a couple final examples. So number 1 here, consider the function, a nice parabola, 4 minus x squared on the interval from 0 to 2. And the first thing I want us to do is, before we actually find the average value, I really want us just to kind of predict a range of values or some bounds on what our answer will be, just thinking about this reasonably. So if I look at, that was kind of sideways. Let's try that again. All right, so if I look at my XY coordinate plane here, and let's just go ahead and kind of graph this parabola, not necessarily drawn to scale, of course. All right, so here's 4, and it's going to have an x-intercept down here at 2. Let me erase that just so I can write that there. All right, so here we're at 2. And when we think about the graph of this function and what the average value really is, it's the average value of that function. It's the average of the function values, or the output, the y values. So, even though obviously this function, keeps going in both directions here, right? We're really just focused on this interval from 0 to 2. So we're just focused on this part of the function. And so think about the range of y values that are represented on that part of the function, and it's between 0 and 4. So here's what I know, just before we get started. I know that my average value when I am done ought to be in between 0 and 4. If it's not, that's a red flag. I've done something wrong. All right, now let's actually find that average value. Okay, so the average value, y bar, we developed this idea last time in a few different ways. So it's the 1 over b minus a, so in this case 2 minus 0, times that definite integral from 0 to 2 of our 4 minus x squared dx. All right, so we have 1/2 times, and taking that antiderivative, 4x minus x cubed over 3, or 1/3 x cubed. And now we need to evaluate between our limits of integration here. So I'm just going to keep the 1/2 out in front of this whole process. So subbing in 2, 4 times 2 would be 8, minus 2 cubed is 8 and then thirds, and then minus, and of course when we sub in 0 to each of those terms, those are both 0. And so we're simply going to have, if I distribute through that 1/2, that would be 4 minus 4 thirds. And so if you think about that, it's like 12 thirds minus 4 thirds, which would be 8 thirds. Or if you prefer, 2 and 2 thirds. 4 minus 1 and 1/3, so 2 and 2 thirds. So this very clearly falls within that range of values that we had predicted, right? So it falls in between that 0 and 4. So this is our value here for, so this right here is our average value. So y bar is equal to 2 and 2 thirds. So if we go back up to the graph, so a little over halfway, so let's say right about there. So let's say that's our 2 and 2 thirds. Okay, so that's the average value. All right, so now let's find the value of u that's guaranteed by the mean value theorem. So what we just found with y bar up there, so when we found y bar, that's the f of u. So y bar is equal to this 8 thirds. And so we're looking for the corresponding input value. So we're setting this 8 thirds equal to our function here. So our function was 4 minus x squared. So we're setting that equal to our 4 minus u, let's say squared, since I'm finding a value for u here. All right, so let's just maybe kind of think in our heads, adding the u squared over here to the left, and then maybe subtracting the 8/3 here to the right. So we would end up with our u squared is equal to 12/3 minus 8/3 would be our 4/3 there. And then taking our square root, generally plus or minus square root. Here we're just kind of in that first quadrant, so we're just going to take our u equals the square root, positive square root. Square root of 4 is 2, and then over the square root of 3. Or if you prefer, 2 root 3 over 3. So this is the value of u, and as you look at your homework questions, they may ask for one or the other, but this is the value of u guaranteed by the mean value theorem. So if we go again back up to our picture here, this value right here, this 2 root 3 over 3, that's the value of u guaranteed by the mean value theorem. And so now what we've really discovered here is that the area of this rectangle that has a width from 0 to 2, so it has the width from 0 to 2, so from the A to the B, and the height of the 2 2/3. So the area of that rectangle, so the area of this rectangle is, and this is not going to be, this is not drawn perfect at all, because when I draw these areas, they're not going to look so equal, but use your imagination. The area of that rectangle is equal to the actual area under the curve. So would have equaled this area. And like I said, obviously this isn't drawn to scale, but those two areas are equal. So that's our geometric interpretation for what we found there. All right, let's look at one last example here. So we have yearly sales in the first 5 years of a company, and that's given by this S of t function. So 0.35 t squared plus 2t in millions of dollars. And here we are asked for what are the average yearly sales for the first 5 years. So we want to recognize in some of these application problems here when we're now being asked for the average value. So here it is, it says we are looking for, so we are trying to find the average, and then yearly sales, it's the average value of this S of t function. So the average of S of t, and well, that means we need over some interval, and if it's over the first 5 years, it's on the interval from 0 to 5. So we are doing exactly what we did right up above there in part B, and so we are finding the average value. So we are going to have 1 over our b minus a, so 5 minus 0, times the definite integral from 0 to 5 of our S of t function. So 0.35 t squared plus 2t dt. All right, so let's go ahead and evaluate here. We have our 1/5, and then taking that antiderivative, it's going to be 0.35 t cubed over 3 plus 2 t squared over 2. Of course, those 2's reduce. And then evaluating between our limits of integration. And so we're going to end up with 1/5 times, and then you'd be subbing in your upper limit of integration. So your 0.35, 5 cubed over 3, and then plus your 5 squared, of course. And so that is subbing in your upper limit of integration. In this case, lower limit of integration again is 0, but subbing in 0. So subtracting 0 wouldn't change anything here. If we wanted to distribute through that 1/5, we would end up with 0.35 times 5 over 3, 5 squared, over 3, and then plus 5. And so if we were to plug that into our calculator, which I did before, we should get approximately 7.9. And this was in millions of dollars. So this is the average yearly sales over the first 5 years. All right, so we'll go ahead and end there. Certainly we can do some more examples in our Zoom meetings this week, but we'll end that last example there.